3 stars, one closed path, going round forever. Nothing acting on them but gravity. Pick 3 stars at random though, and you get this. That first one is exact. It repeats forever. And nobody has ever found one out there. There are hundreds of them, and the sky doesn't contain a single one. So where are they? 2 stars is a solved problem. Any masses, any starting point, you get an orbit that repeats. And we have known that for 300 years. Add a third and it's gone. There is no formula anymore, and there will never be. That's proven, not just difficult. It is still completely determined. Same setup twice gives you the same thing twice. But move 1 star by less than the width of an atom, and a few loops later, your 2 runs have nothing to do with each other. So in practice, you can't predict it. You can only watch it. Except a handful of starting points don't fall apart. Get them exactly right and the whole thing closes up and runs forever. This one was found in the 90s. That one is the butterfly. And there are hundreds more. You can stumble onto them, by the way. Pick a starting point at random and your odds are essentially 0. They only turned up once computers could grind through millions of setups looking for the rare one where all 3 stars come back exactly where they started. So there is order in there. Which brings me back to the thing that bothers me. If these exist, why has nobody ever seen one? Here is my first guess. Every one of these got a perfect start, and space doesn't hand those out. A star wanders past, a bit of gas drifts through, and your starting conditions aren't the ones that closed anymore. So let me lean onto them and see what happens. Before I do, you should know what's actually in here, because it's the only reason the result means anything. Where each star is, how fast it's going, and gravity pulling between them. That's the lot. No collisions, no gas, nothing I've tuned. So when one of these falls apart, I can't blame it on anything I put in there. The only thing arriving from outside is my push. And I will tell you every time, same push on all 6, and I keep winding it up, and they start dropping. But look what's still going, the figure 8, and the butterfly, right there with it, long after the rest have gone. Push hard enough, and even those 2 give up. Nothing here is immune, but those are the tough ones, and it isn't close. And that's the pattern across the whole zoo. Somebody went through more than 1,000 of these and checked. 23 properly stable, 500 odd marginal, 781 that simply come apart. Surviving a knock is the exception, so the figure 8 is the toughest one on that grid. And then I tried the other test. I'm making 1 star heavier, that's a minute change. I have exaggerated it 12 times over so you can see anything at all. And the orbit is finished. It needs 3 stars matched to about 1,000%. Nothing forms that way. A collapsing cloud gives you whatever masses it gives you. So there's my answer, I thought. Beautiful, tough, and impossible to build. Except that's wrong. And I want to show you why. Because the obvious question is, what if you stop insisting the stars are identical? And people did exactly that. In 2021, a group took one of these orbits and pushed it sideways into unequal masses, one small step at a time, and came out with 135,000 of them. 30,000 are stable, properly unequal too, the same sort of ratios as a real triple somebody has actually measured. So these you could build. The stars exist. My mass argument is gone. So I put one through the first test. And it went early. The figure 8 is still tracing away, while this one is already finished, which is the shape of the whole thing. Gain on one test, lose on the other. Every one of these orbits is stable inside a narrow window. You have to get the masses nearly right, and then nothing can be allowed to jog them. So, now look at what this guy actually has. Triples are common enough, and they are all built the same way. 2 stars close in together, and a third one a long way out, going round the pair. And look at what that really is. Those two are so close that the far one barely registers. They are just doing an ordinary two-body orbit. And from out there, the third star can tell there are two of them. It feels one lump of mass and goes round it. Two two-body problems, one inside the other. So I shoved it. Same test. And it just takes it. The orbits stretch, they don't go back to what they were, nothing does. But it stays bound. Still a triple in a billion years. And the masses? It doesn't have a window. Two-body orbits work for any masses at all. And this thing is two of them stacked up. Make one star twice the other, 10 times, it carries on. That is the answer. It is better on both counts by a mile. And everything in that zoo is squeezed into a tiny corner, needing you to get two separate things right at once. And nature does try the other thing. Young clusters are full of triples when nothing is paired off yet. 3 stars roughly the same distance apart, all pulling on each other. They tear themselves apart. 2 pair off, the third one leaves at speed and doesn't come back. And what's left is a tight pair with a distant third. Which is the answer again. It builds the stable thing by wrecking everything else. So that's where I've got to. 2 stars solved forever. 3 that really pull on each other, and the maths breaks. And buried in the break are thousands of exact answers, some of them genuinely stable. They are just stable in a fuzzy way, whereas a pair with an outsider is stable in a stupid, forgiving, any old stars way. So when a cloud collapses and drops 3 stars down at random, that's overwhelmingly what you end up with, which makes the other kinda rare. It doesn't make them impossible. 13,000 of those orbits are stable and would work with stars we've already catalogued. And as far as I can tell, nobody has properly gone looking. Gaia has measured 1.5 billion stars. One of these might be sitting in that data right now.